Hello, uh, Dev, are you there?
Yes, sir.
Okay, so we'll start off. The first thing that we look at is this selection of one or more objects from n different objects. So basically, the point is that there are n things, and you have to select one or more out of these n things. One or more. There are n different things. You could select one, or you could select two, or so on, right? So how many ways can you do this? Think about it. How many ways can you select one or more things? If these are n different objects. So we are underlining the different objects part because that is crucial. Because if you
Yeah.
were doing the same thing, selecting one or more objects from n identical objects, that would
Mhm.
be completely different.
Hmm.
Like
Yeah.
here, if I have A, B, C, D, E, these are the n things, five things. And if you select one or more letters out of this, will number of ways to do that will be different from if I had A.
Correct.
So how do we count this? This will
Total are n, so it'll be NCR, right? Like,
no, this is one or more.
okay, so
You could select one, or you could select two, or you could select three. You have to, because it is a or question, you have to add, right?
so we have to write NCR plus NCR minus something like that.
Yeah.
NCR plus n minus one CR minus one.
No, no.
Uh, okay.
How many ways to select one object out of this n things?
One object NCN.
Select one object out of n objects. It's
Hello.
NC1, no?
Yeah, sorry, NC1, correct.
Yeah.
Hello.
So,
Yes, sir. Am I audible?
yeah.
Okay, sir. Yeah. Sorry, sir. There was some network issue, so I got disconnected.
So select one object out of this is NC1. Select two objects is what?
NC2.
NC2.
And total finally select n objects is NCN. So this is selecting one, this is selecting two, three, and so on till n. These are the possibilities. Because it is or, so you are adding, right?
Right.
Yes.
So this sum will be what? By binomial theorem, you can easily say this sum.
Just a second.
Find out the value of this sum. This is not hard. Binomial theorem, if you remember, this is just C1 plus C2 plus Cn.
2 to the power n minus 1.
Yeah, because C0 plus C1 till Cn was 2 to the power n, right?
Correct. So, and then 1 plus so.
Hmm. So this is basically 2 power n minus 1. So if someone says select one or more letters out of these A, B, C, D, E, then it can be done in 2 to the power 5 minus 1 or 31 ways.
Yes.
Why? Because you could select one letter in 5 ways, right? one letter.
Yeah.
You could select two letters in 5C two ways, right? You could select three letters in 5C three ways, four letters in 5C four ways, and all five letters in one way, right? Correct. 5C2 and 5C3 are 10, and this is
Correct.
5, and it's adding up to 31, right? Correct. You can also think of this selection in a slightly different way. You can think of selecting one or more objects out of n different objects in a slightly different way by thinking of your selection. So this is object 1, this is object 2, object 3, and this is object n, right? So now when you are making a selection, you have to make a decision about each of these objects, right? Like while making your selection, you'll have to decide, right, that first object whether to select or not, right?
Yeah.
So you can either select it or reject it, right? So there are two choices, right? Two choices for the first object, correct? And there is
Right.
two choices
Right.
for the
Right.
second object and third object and so on, right? And to make a selection, you have to make all of these choices. You have to make choices for each of the object, right? While
Yeah.
making your own selection, you can either select or reject each of these objects. So now this is a breaking down the task into subtasks, right? This is to make a
Correct.
selection, you have to make a selection about each object, right?
Yeah.
So this is a multiplication principle. Like each subtask must be performed to do the ultimate task, right?
Hmm.
So this is 2 into 2 into 2. These are the choices for each object. So this is 2 power n. 2 power n is coming, is the total number of choices. However, this includes a choice where we have rejected all of them, right?
Correct. So
There,
-1.
so there is one choice where you have rejected everything. So that means you didn't select anything. So that you can exclude. So 2 power n minus 1 will be the total number. So
Got
what
it.
we are seeing here is two different ways to do the same thing. One is by addition principle, where you are saying nc1 plus nc2 till ncn, because you are selecting either 1 or 2 or 3 till n, right? And one
Correct.
is by multiplication principle, where you are saying the the job of doing that selection can be done by selecting or rejecting each of these objects. So you have 2 power n total ways to do this, and minus 1, so that you don't reject everything,
Yeah.
right? So multiple approaches, you can do the same thing. So now suppose the question is number of ways to select at least two objects. Number of ways to select at least two objects from n different objects. From n different objects. That would be what? At least two you have to select from n different.
So that'll be NC2 plus NC3,
And
so on till NCN.
hmm, uh, so you have to basically say you can do 2 power n minus 1 minus
Minus
nc1,
NC1. Correct.
right? So that is basically nc2 plus nc3 and so on till ncn. So basically the answer to this would be 2 power n minus 1.
Right.
right? Okay. If similarly, if you have to select at least R objects, right, out of n different objects, same idea again. It's just that you start from R, right?
Yeah.
You have to do NCR plus NCR plus 1 plus so on till
See, yeah,
NCN. So this sum, whatever it comes, that is the answer, right?
correct.
So this is selections from different or distinct objects where example was different letters. You can easily distinguish between the letters. So each letter combination, basically a BC is different from CD, right? If I was selecting two, then
Correct.
this selection is different from this selection.
Correct.
However,
Yeah.
if you have now n identical objects, and the question is select one or more from them, one or more objects from n identical objects. So how many ways can we do this, right?
Yeah.
Think about it. So take an example and think, say if there's say four A's, right? You have to select one or more A's out of this, right?
Yeah.
Yeah.
So suppose you have to select one A, right? How many ways can you do this?
4.
No, there's only one way, dude.
Oh yeah, 1 we have to select. Correct. Yeah.
Yeah.
No, it's not four. Why is it not four?
Because you have to choose 1.
No, that is not the reason. Because all the A's are
All of them
identical.
are same, right?
Oh, right,
That's
right,
why.
right.
It's not because you have to choose one.
Yes, yeah.
If it was A, B, C, D, and you have to select one thing, that would have been four ways
Yeah, 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 got it.
because they are different things.
Yeah.
Right now, it is only one way. If I have to choose two A's, how many ways are there? Two things out of these four A's.
Um,
2 is.
No, it's
there'll
still
still
one way.
be one way, right?
Yeah. How are there two ways?
Oh,
Aditya, why two ways? What
Uh,
are the different ways?
okay, all of them are same.
Yeah. What is the difference between one way and another way?
Yeah, all of them are same.
All of them are identical. There is no other way.
Correct, correct.
If
Yeah,
it was at different things, then 4C2 was coming because 4C2 was coming because AB is different from BC, is different from AD, is different from AC, is different from everything, right?
right.
All of
Yeah,
these are different from each other.
yeah, understood. Yeah,
What is the difference here? There's nothing here.
correct.
There's only one way. Similarly, 3A's also there is only one way.
Yeah,
And
yeah,
4A's also there is only one way,
yeah,
right? So actually in each, when there are identical objects, the number of ways of selecting one or more will be just 1 to n. All the possible selections can be done in one ways.
yes.
yeah,
Like selecting one out of them is also one way, two out of them is also one way, and n out of them is also one way. So total answer will be n here, right?
yes.
Correct.
So select, suppose the question was instead of that, select R objects from n identical objects. R objects from n identical objects, right? How many ways can you do this? Now it is not a sum of one or more, it is just exact value, r way objects from n identical objects.
Yes.
So how many ways will you be able to do this?
This will be one, right?
Hmm. It is one. I hope you guys are understanding why.
Yeah.
One specific number, right? But it doesn't matter because everything is same. You just have to count out those. So R is 2, for example, out of n is 4 here. 2 A's out of 4 A's is one way only, right?
Yeah.
Yes.
Are you understanding or are you saying yeah, just like that?
No, I got it.
Okay.
No, sir, I understood.
Suppose selecting 0 or more objects out of these n identical objects. So then what will happen? 0 or more. Selecting 0 or more objects out of these n identical objects. So it is related to the first one where you have to do one or more. Here you have to do 0 or more.
Mm, this will be n plus 1.
Hmm. This will be n
Yeah.
plus 1. This is important because think of a situation like this. Suppose you have 12 is equal to 2 power 2 into 3 power 1, right? So how do you count number of factors of 12? Number of factors of 12. For that, what do you have to do? You have to take powers of, you have to select two. Powers can be 0, 1 or 2, right?
Yes.
And 3 powers can be 0, 1, right?
Correct.
So number of ways to select 2 can be 0 or more 2's you can select out of these, right? To count factors,
Yeah.
you will have to count the number of 2's in the prime factorization. No? So
Yeah.
the
It's n
number
plus
of
1,
ways to
right?
select 2 will be 3, right? And the number of ways to select 3 will be 2. So there will be 6 factors. Do you understand? Including itself and 1. 6 factors
Correct.
which will include 2 power 0 and 3 power 0 and also include 2 power 2 and 3 power 1. Are you understanding?
Yes, sir.
So for example, find the number of factors of say 72, right? Number of factors. So I will do the prime factorization of 72, which will be 9 into 8, so 3 square into 2 cube, right?
Correct.
Now, number of ways to select 3, and each 3 is identical, right? There is no difference between one 3 and another 3, right? So selecting 0 or more
Yes.
3's out of 2 3's, right? That will be, so basically the question is select 0 or more 3's out of 2 identical 3's, right? Correct.
Yes. Yes.
Multiply it with selection of 0 or more 0 or more 2's out of 3 identical 2's, right? So this can be done in n plus 1 ways, right? 2 identical 3, so you can do 3 ways.
Yeah.
and this can be done in n plus 1
4.
ways. So 3 plus 1, 4 ways. You'll get total 3 into 4, 12 factors.
Yes.
12 factors includes factors like 3 power 0, 2 power 0, and also 3 power square, 2 power 3. So 1 and 72 are included in this. If you want to do a proper factor, then you can exclude 72, and then that will be the number of proper factors, right? The number itself is not a proper factor, right? Are you understanding?
Yes, sir.
Okay. Then, so again, extending the ideas discussed earlier, number of ways of selecting at least two objects out of n identical objects. Would be how much? One or more we had done, right? That came out to be n, right?
And yeah.
So now you have to do two or more.
Will this be n minus 1?
Hmm. That will be n minus 1, because you can select 2 in one way, 3 in one way, and so on till n
Correct.
one way.
Correct. Correct.
So the sum of these numbers, the total options are basically n minus 1, right?
Yeah.
So number of ways of this gives us at least number of ways of selecting at least r objects, selecting at least r objects out of n identical objects, that comes out to be basically n minus r plus 1. Try to think about it. This should be
Yeah.
understandable.
Yeah. Correct. Correct.
Okay.
Yeah.
Aditya, you are understanding, right?
Yeah.
Okay. Then the total number of selections, of some or all out of p plus q plus r objects, where p are of one type, q are of another type, and r are of third type, and each type objects are identical. Okay, that will be
Yeah.
how much? So basically you have p objects of one type, q objects of another type, and r objects of another type. So it is like this: a, b, 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 and c, 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 c. So 4 a's you have, 2 b's, you have 5 c's, right? Now the question is saying total number of ways of selecting some or all out of this many objects, right? So you have to select some. So that means you cannot reject everything. Okay. So you
Right.
can think about it, and first basically do this. First find out total number of ways of selecting or rejecting a 0 or 1, 0 or more for all of the objects, and then subtract 1 from the case where you have rejected everything. Think of this specific case and try to figure out the answer. How many ways can you select something out of this? One or more things out of these, right?
Hmm.
Or maybe easier would have been number of factors of 2 power 4, 3 power 3, 5 power 5. Find out number of factors of this.
That will be 120, right?
Why?
Because
You're
of
doing
the
5 into,
4 into 6.
you're doing this, right? So what are you really doing? You are saying select one or more twos, right?
Yes.
That can be done zero or more twos, right? Not one or
Yeah,
more twos.
0 or more. 0 or more.
Zero or more
Correct.
twos can be done in 5 ways. Zero or more threes can be done in 4 ways. And zero or more fives can be done in 6 ways, right? And you are multiplying because that is the total number of ways of selecting. You have to do everything. And then you should subtract 1 if you have to select a factor which does not exclude everything, right? If you are excluding that factor of 1, right?
Right.
1 is the factor which has 0 2s, 0 3s, 0 5s, right?
Correct.
So similarly, in this case also, there are p objects of one type. So number of ways of doing that would be p plus 1, right? 0 or more, right?
Yes. Yes.
q plus 1,
Oh, okay. Right. Got it.
r plus 1, minus 1. Basically, you are either selecting or selecting 0 or more out of the one type of objects, then 0 or more out of the q type, and 0 or more out of the r type, and then subtracting 1 for the case where you did not select anything, right?
Correct.
It's the same idea. It's just combined. If there are multiple types of objects, then you have to do all of those things. No, it multiplication principle comes
Correct.
because there are not just one type. There are 3 types. So you have to do that multiplication, right?
Yeah.
Okay. We'll look at some questions. Uh, okay, before that, one last thing. Uh, so suppose you have to do number of ways of selecting one or more objects from p plus q plus r plus n objects where p are alike of one kind, q are alike of second kind, q are identical of second kind, and so on, and r are alike of third kind, and the remaining n are different, are distinct. Okay. So what has happened here? Here there are 3 groups of things which are p, q, r things, right? And then there are n different
Yeah.
things, right? You have to find number of ways of selecting one or more. It's the same question plus the original idea of this part we had done separately earlier. How many ways are there of selecting one or more things from the 2 power nth different things, right? That was 2 power n minus 1.
Yes.
So if there are p things, number of ways of selecting 0 or more out of p identical things will be p plus 1, right?
Yes.
Number of ways of doing 0 or more from here would be q plus
Q
1,
plus 1.
and this will be r plus 1.
And
But
then,
what about the n different things? 0 or more out of the n different things would be 2 power n, right?
yes.
And total number of ways is
Minus 1.
0 or more minus 1,
Correct.
right? So here you have selected 0 or more and you're subtracting 1 for the case where nothing you have selected, right? Does it
Correct.
make sense? It is combining the ideas from before, right?
Yeah.
So suppose I make a change in the question and I say I have to select at least one object each of each kind, at least one object of each type, and one from the n different, right? N different objects also. Then number of ways would have been what here? I have to select one at least from this, and this types, and one from the n different groups.
Mm. Um, so for this, we'll have to do NC1 plus NC2 and then into 2 raised power n. No, this sounds wrong. Just one minute, sir.
No, I mean, think of if I had to select at least one from p objects of same kind, right? How many ways can you do that?
N plus 1. P. No. It's
There are p objects of one kind, and you have to select one or more out of that. Let's say p is 3. There are 3 a's. You have to select one or more a's out of this. How many ways can you do it?
1.
You have to select one or more a's. So
Oh, 1 or more is. So we can do that in
selecting one a can be done in how many ways? Here, out of 3 a's. Can be done in one way only, no?
Yeah, one way.
And two ways
Also one way.
and three ways.
Also one way.
Total number of ways is what?
3.
There are p ways to do this.
Yeah. Then Q ways to do that in R ways. Okay. Yeah.
We had discussed this no earlier.
Yeah, yeah.
P
Yeah,
plus
right,
1
sir.
was the number of ways of selecting 0 or more, and p is the number of ways of selecting 1 or more.
Yeah.
And if at least r you have to select, then you would have to do, out of n identical things, you have to do n minus r plus 1,
Yeah.
right?
Yeah.
P ways to do this, q ways to do this, r ways to do this, and you have to select one out of the remaining n also, right? There are n things, you have to do one or more out of that also.
Yeah.
So that will be 2 power n
And
minus
minus
1.
1.
This product is the answer then, pqr into 2 power n minus 1. Instead
And
of p plus 1, q plus 1, r plus 1, 2 power n minus 1,
yeah.
you have pqr into 2 power n minus 1.
Right. Okay, got it.
Here there was no restriction. You could select 0 of this also, 0, 0, 0.
Yeah. Yeah.
Are you understanding all of this so far, what we have done?
Yes, sir.
Yes.
So there is a difference when you have different objects, that is fairly easy. And then there is identical objects. So different objects, suppose there are n in each case. If you have to select 1 or 0 or more, you have 2 power n, right? If
Right.
you have to select 1 or more, you have 2 power n minus 1, right? If you have to select r or more, you have to do ncr plus ncr plus 1 plus ncn, correct? Here the same thing, 0
Right.
or more ways, it is n plus 1, 1 or more is n, r or more is n minus r plus 1, right? Correct?
Correct.
Correct.
Is everyone understanding this difference?
Yeah, got it.
Now, the only thing in the other questions that we saw is that there were p of one kind, q of another kind, and r of another kind. And there were n different objects also, n different other objects also. These were identical objects. So the number of total ways of selecting 0 or more things would be p plus 1 from here, q plus 1 again from there, r plus 1, and 2 power n from here, right? Minus 1 if you have to select one or more, right?
Correct.
Correct.
Without any restriction, this is one or more without any restriction. It could be any one, right? Your the case where you have just one thing, it could be any one thing, right? Here there is no restriction. You're just excluding the case where you selected nothing, right?
Yeah.
However, if you have to take one of each kind as well, right? One of each kind, right? So you have to select one out of this at least, right? So that will be n, no, here, correct?
Yeah.
Correct.
So it will be p, q, r, and you have to select one out of this also. So 2 power n minus 1, right?
Yeah.
Suppose the question was different. You have to take 2 at least out of P, 3 out of Q, and 1 out of R at least, right? And no restriction on this, right? You understand?
Yeah.
At least 2 out
Yes.
of P. So I would do at least 2 out of P. So R or more out of P. So, right? So P minus 2 plus 1, right?
Correct.
So it would be P minus 1, right? Into 3 at least out of Q, right? So
Hmm.
Q minus 3 plus 1. So Q minus 2 and 1 of this, right? So that would be R and no restrictions on this, 0 or more, right? So that
Yeah.
would be 2 power n, right?
Correct.
So that would be the number of ways to do that particular question. Are you getting this table?
Yeah. Got it.
So you have to recall this, like this is the distinction and this is how you combine cases, right?
Yeah.
I hope this you have written down somewhere.
Yeah.
Yes, sir.
Okay. Uh, then we'll look at some questions now. Okay. Okay. So first question is number of ways in which one or more letters can be selected from A, A, B, B, C, D, E. Find the answer. Is it difficult, this one?
No. No. Just a second. Is it 159?
Hmm. There is no restriction. You can do 0 or more, 0 or more, 0 or more, and minus 1, right?
Correct.
So 0 or more out of these 4 A's can be done in 5 ways. Out of these 3 B's can be done in 4 ways. And 0
Then
or more out of this can
2
be done
cube
in 2 power 3.
and
And
then
then
the whole thing
minus 2.
minus 1. Yeah.
That will be 159, right?
Yeah.
Dave, are you understanding?
Yes, sir. I got the same answer.
Okay. Then now question is an exam paper has 3 sections, has 3 sections A, B, C. There are 6, 4, and 3 questions. 6, 4, and 3 questions respectively in the three sections. Respectively. In the three sections, student has the freedom to answer any number of questions, attempting at least student can attempt any number of questions, but has to do at least one from each section, right? How many ways can the paper be attempted by the student? Can do one from each section. He has to do one from each section. How many ways can the paper be attempted?
Mm.
Remember that questions are not identical, right?
Yeah, yeah.
So don't do the calculation, just tell me the expression. Questions are all different, and doing a question from section B is different from doing a question from section C, and so on, right?
Yeah.
So
Yeah.
at least one from each section. So there are 6 questions which are different in each section. So it will be 2 power 6 minus 1, right?
Plus 2 power 4 minus 1.
Not plus, it is multiplication.
Okay, he has to
Yeah,
do. Yeah, he
multiply.
has to do. Yeah, okay. Yeah. Multiplication, correct.
This should be the answer.
Yeah.
Correct, got it.
It is multiplication because all three he has to do. It is not like or,
Yeah, yeah, yeah.
right? So this will be the answer, whatever is the answer from there. Okay.
Right, right, right. Understood.
Then the next one is uh okay, next one we have already discussed number of prime factors and all. So basically, if there is a number n and n is written in terms of prime numbers like this, p1 to the power k1, p2 to the power k2, and so on, pr to the power kr, right?
Hmm.
P1, P2, P3 till PR are distinct prime numbers, and K1, K2, KR are positive integers, right? So how many positive divisors are there? Number of divisors. Number of divisors is fairly simple. You have to select 0 or more prime factors, right? Out of the K1 P1s, you have to select 0 or
Yeah.
more, right?
Yeah.
You have to do K1 plus 1, right? That
Yeah.
is the number of ways into K2
K1
plus
plus.
1,
Yeah.
multiplied so on till Kr plus 1.
Plus 1. Yeah.
This can be written as product of I goes from 1 to R, kr plus 1, right?
Hmm.
That will be k1 plus 1 into k2 plus 1
There
into
should be
so
ki plus 1, right?
ki plus 1, ki plus 1. Total number of divisors is always going to be this.
Yeah,
This includes 1 and this includes the
number
number
itself.
itself. Okay. Then question is, how many ways in how many ways can three letters be selected from A B B B C? Okay, this is the question. How many ways can three letters be selected from A B B B C?
Yeah.
So understand that there can be several types of three-letter combinations here. Like the final selection that you make could have all three letters different, all three letters identical, two identical, one different, right? There are several cases to consider here. All letters are identical. You are selecting three letters and all are identical. That can be only done using the three B's, right?
Correct.
Correct.
That is one way. How many ways to select three B's out of three B's, right?
Yeah,
One way.
Yeah.
one way.
Then you can have two are identical and one is different, right? Two
Yeah,
are identical and one different. So two identicals, you have two options, right?
yeah, AAC or BBC or BBA.
You can do AA or BB,
Yeah,
right? Either you can select two identical A's or two identical B's. So there are two options for that. And then after that, if you selected one of those identical ones, right? You have to select one more letter out of the different letters, right? So there are two options for selecting the other letter also, right?
correct.
Like if I selected the two A's, I can do B or C.
Yeah.
If I selected the two B's, I can do A or C,
Hmm.
right? So
Yeah.
that will be two ways. So total number of ways here will be four. And case three is all are different, right?
Yeah.
Right.
So you have to select one A out of this. That can be done in one way. One B out of this, one
One
way,
way
and one
and
way.
one C. Yeah, so one way.
So the total number of ways will be six, right? One plus
Hmm.
four plus one. Why
Yeah,
am I doing addition here? You can do either this
yeah,
or this or
correct.
this. right?
Yes.
So therefore, addition at the end.
Yeah.
The total number of ways will be 6. So whenever such questions are there where you have to select objects from a collection of things where some could be identical, some could be different and all, it is good to take cases and do it. Okay, take cases where some are identical, some are different, and so on, right? So for example, another question like that, try this one. How many ways 4 letters can be selected from? 4 letters can be selected from the letters of the word ineffective. Ineffective. Okay, again, construct your cases here. Okay, there are 3 E's, 2 F's, 2 I's, and C, T, N, V are different.
Yeah. So we can select three same and one different.
Hmm. So
So
case one will be
three same and one different. So for that we have four possibilities.
3 same
No,
can
no,
only
no,
be
no.
done in this way.
Yeah, I mean like for the one different.
For the one different, there are how
One,
many
two,
possibilities?
three, four, five, six.
6 possibilities, right?
Yeah, I forgot the F and I.
So the 6 ways for case one.
Yeah.
Then case two is what?
Case two is two same and two different.
You can do two identical of one type, and you can
And
also
two
do
identical of other type, correct.
two identical of other type. So two identical of one type you can choose out of these three, right?
Correct.
Basically, you have to select two out of these three, right?
Yeah, yeah,
And you have to select two of each, right?
yeah.
So that will be done in 3 ways, right?
Yes.
You can do either EEFF or EEII or FFII, right?
Yeah,
So this can be done in 3 ways, right? Two identical of one type, two identical of other type, right?
yeah.
Then you can do case three, which is two identical of one type and two different, right?
Hmm.
Two different letters. So this can be done in how many ways?
Uh, First selecting two identical of one type will be three again.
Hmm.
And then and then there are 7.
7. Oh.
Because like let's say if we select E and D,
Hmm.
so then of 4 letters can be selected. Okay, fine. Wait. I messed up. No, wait. So yeah, so if we select two E's, then there'll be one E and then two F's, two I's. We can select any of all of them remaining, right?
Mm-hmm.
Similarly, if we select two F's, then there'll be three E's, two I's, one C, one T, one N, and one V.
You have to select two different. So,
Okay. So we can't take the same letters.
you cannot take the same letters. See, one type, once you select one, two identical thing, then after that, you have six different letters.
Correct. Correct. Six different. Correct. Yeah, got it.
Four here and two
One
here.
each here. Yeah.
Six letters out of which you have to select two.
Yeah.
That can be done in 62
You
ways.
too. Yeah, correct.
Dave, are you understanding?
Yes, sir.
Three ways to select any to do identical, and six ways to select out of the remaining six letters. Two ways to select, 62 ways to select that.
Yeah,
So
got it.
this will be 3 into 62, so 3 into 15 is
15.
equal to 45.
Yeah,
And case 4 is all different, right?
correct.
All different letters. So there are how many letters are there different?
1, 2, 3, 4, 5, 6, 7, 8.
No, there are seven letters, no, which are different.
Okay, I counted wrong. 7.
Seven letters are there. You have to select all different. So
See,
7C4,
yeah,
that will be 35.
correct.
The total number will come out to be 6 plus 3 plus 45 plus 35, right?
Yeah,
So this becomes 89.
yeah, 89.
That is the total number of ways to do this. Are you
Correct.
understanding?
Yeah,
Yeah.
So you have to do by cases in these type of questions, and you have to think carefully of each case. One last question of this type. Uh, let's see, in how many ways can a child select five balls from select from five red,
yeah,
four black, three white, two green, and one yellow balls. Balls of the same color are identical. You have to select five balls.
yeah, just 2 minutes.
Are you guys getting the cases here?
Yeah, we can choose first case is 5 identical balls. That's only one because all red.
Hmm.
Then we can the case two is 4 identical and one different.
Okay.
So choosing 4 identical, we can do it in two ways. Either we can choose 4 red or 4 black,
Two ways into.
and then we have to choose 4 more balls out of
So one, two, three, and
three.
one.
Yeah,
Four,
so four.
right?
Correct, into four.
So that
No,
will be total eight,
correct, into eight. Yeah, becomes eight.
right? Dave, are you understanding?
Yes, sir. Yes, sir.
Case three,
It can be 3 identical and two different. No, two identical.
three identical, two identical is also a case.
Correct.
Yeah, yeah.
That can be done in
Three
one, two,
identical,
three, the three identical in 3 ways, and two identical in 4 ways. No,
one is left
one will left. Correct.
and there are three again.
Yeah, so three into three, 9.
So nine ways. In case four,
Case
is
four can be
three
three
identical,
identical and two different.
two different. Three identical again, three ways.
Yeah,
And
and
now how
two.
many different things are left? Two from here and two from here, right?
Yeah, yeah,
Four out of
Four.
four, you have to select two.
correct. For C2.
So three into six, this is right. Four by, no, no, it is
Factorial
12. Right?
3 into 4, 12.
No, no, it is six.
4 by 22, and yeah, it'll be 6.
So three into six, 18, right?
Yeah,
Then case five, two
two
identical,
identical and three different.
two identical, one different. That is
Okay, yeah, yeah, yeah. I missed that case only.
so two identical.
Color can be chosen in 4 ways.
No, out of, so one second. So you have to select two groups of two identical, right?
Yeah.
Out of four possible
Oh,
identical
okay.
groups.
Yeah. So
Four C2
4
ways to
C2
select
again.
the thing.
Hmm.
And once you have selected two, you have three things left then, three types of things left. Out of the four possible identical,
Yeah, one will, yeah, three will be left. Correct.
you have to select one from there. So that
Yeah.
is three ways.
Three, yeah, 3 ways.
Yes.
So this is again 6 into 3, 18, right?
Yeah.
Then you have case 6 is two identical and three different, right?
Correct.
Two identical you can
Yeah.
choose in four ways, right?
Yeah, and three different we can
Correct.
choose in
Four ways again,
four.
because
Yeah,
once you choose one,
Yes.
after that you
correct.
have four things,
Four will be left. Yeah.
right? So it
16.
will be 16 here, and last case should be all different.
Yeah.
All different would be five balls from five groups, right?
Yeah.
Only one way.
One way. 5C5. Correct.
So the answer will be 9 plus 18. So 36, 54, 71, right? The total answer is 71.
Correct. 71. Got it.
Okay.
Understood.
Then
Yeah.
let's look at some different types of questions. Uh, okay. The question is, in how many ways, in how many ways can can we select can we select two unit squares on a chessboard, on a chessboard such that both squares both squares are Neither in the same row nor in the same column. Right.
Hmm. Hmm.
Chessboard has 8 cross 8, so total number of squares is 64. So you have to
Yep.
ensure that your selection of two don't lie in the same row or same column, right? So if you think about it, let's draw the chessboard. 1, 2, 3, 4, 5, 6, 7, 8. This is a chessboard 8 cross 8. So normally, if there was no restriction, I could have 64 squares are there, and I would have total number of ways of selecting two would have been this.
Right.
Number of ways of selecting two. Each square is different because you can label them as numbers. 1, 2, 3, 4, 5, 6, 7. Oh wait, so you should 0. Uh, how many are there? 3, 3, 6, 2, 8. Okay, fine. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And the
We
labeling
can subtract the cases of those in which they are from the total, right?
uh,
We can subtract the number of cases in which they are in the same row or same column from the total number of cases.
that could be one way. However, it might be complicated to do it like that. So think about however you want to do it could be fine, but just make sure that you're counting it correctly.
Hmm.
Here, you what I'm saying is that each square can be labeled the uh, by the row and column number, right? So let's have a convention that says each square will be labeled by the coordinates of this point,
Hmm.
like the bottom left of it, right?
Okay, yeah.
So then this square will be called 1, 1, right?
Hmm.
This y-axis is also 1, x-axis is also 1. This square will be called 2, comma 1, right?
Correct.
This square is basically 2, comma 1.
Yeah.
This square is 1, comma 1, right?
Hmm.
So basically you are getting different labels for each, right? This square will be 8, comma 1,
Correct.
Yes.
and this square will be 8, comma 8, right?
Yeah.
So these are different squares now with labels. Everyone's label is their left hand coordinate, this coordinate.
Right.
So, okay, so then let's think about the question then. So you could do it in this way. Uh, you could select first square in the beginning. Anywhere you can put that first square, right?
Yeah.
First square can be selected in 64 ways, right?
Correct.
First square. Now you have to think about where to put the second square, right?
Hmm.
So you have to ensure that the second square is not in the same row. Suppose I put first square here, right? First. I have to ensure it cannot be in this row and cannot be in this column, right?
Yeah.
Right. So I have to exclude this, and this itself, obviously. and this, right?
Yeah.
Correct. So for the second square, right? Correct.
Yeah.
So 7 I have to exclude here, 7, in here 7 and 1, right?
Hmm.
So basically 15 I have to exclude, right?
Yeah. So
49.
49 ways.
49 ways there could be of choosing the second square.
Yeah.
Yeah.
So it should be 64 into 49 ideally,
Correct.
right? However, that answer is wrong, uh, in the sense that the answer is double of what we want. Answer is actually 1568, and 64 into 49 is double of that. So,
So we need half of this.
so some repetition has occurred. So we have to think about what kind of mistake we have made in this calculation. Uh, oh, so the repetition could be, if I chose the, okay, 1 second. Uh, Select two unit square on a chessboard. Same row. So this square I have selected, and this square was 6, 5, 6, 5. Then I can select any other square here and all. Oh, 6, 5. Oh, I think order of the selection doesn't matter, no? Like in the sense that 6, 5 square and say this square, right? Which is a legitimate square, 5, 4.
Hmm.
This is a
Yeah.
legitimate selection. They are not in the same row or the same column, right?
Yeah.
So this selection, are we counting this and this as double? Like, are we counting double like this? Is the point.
Six. But they both are different squares, right?
No, I'm saying ki is our count here including this also and this also?
Oh, okay. Yeah. Okay.
Is the count here including that number and this is the same selection?
Correct. Correct. They both are same.
This is the same selection of legitimate squares. Are we counting double is the question. So maybe a way to understand this would be making a smaller thing, 4, 4 or something, right?
Hmm.
So let's,
So 16 ways for selecting the first one.
so normally I would have said 16 ways of selecting this one. And once you put one, you can exclude 1, 2, 3, 1, 2, 3, and 1. So 3, 3, 6, 7 you can exclude, right?
Yeah.
3 from here, 3 from here, and 1 here, right?
Yeah.
9, right? So I'm
Yeah.
saying 144 according to multiplication principle. But now we'll actually start by putting the squares, right?
Correct.
Like, let's call these as A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? So let's start listing out some of the ways, right? So
Yeah.
A could be there. Suppose I selected A, then I can select any out of these 9, right?
Correct.
Right? So A can have partners with AG, AF, AE, oh,
JKL and MN.
and so on, right? 9, right? I
Right.
selected D. Oh, okay, okay. And it is obvious you'll get multiple times.
Yeah,
Counting
because
double.
yeah,
Because
some it will.
when you do G, you will select A again. No?
Yeah, we will.
Yeah.
You're counting double clearly,
Yeah, got it.
Correct. Correct.
right? So uh, if you do G, you will have GA also, GB also. No, not GB, but
GA will have.
GA definitely comes once more.
Correct, correct. So there is a double.
Right. Right.
So
Yes.
this divided by 2 got it.
So 144 by 2 will be the answer 72. So in this case
Hmm.
also 64 into 49 by
By
2,
2.
32 into 49. So 32 into
49.
50
Yeah.
is
Uh,
32
32 into
into
50
50 is
is
1600
1600, correct.
minus 32.
Minus 32, which is 1568.
That is the answer.
Oh, yeah, 1568, correct.
Okay, so
Yeah.
you have
Got
to
it.
be careful about these repetitions and all. Sometimes the obvious way could have repetitions while the question meant that select any two squares, right? The question didn't mean ordered pair, right? Select any two squares, right? The question was saying. So then A and B selection is the same as B and A selection, right?
Correct, correct.
The question did not distinguish between ordered pairs, right?
Hmm.
So the multiplication principle is giving you the total number of ordered pairs, right? Because remember in the beginning when we talked about multiplication principle, we had written that it is A cross B type of situation, no?
Yeah, Cartesian product.
Multiplication principle A cross B was NA into NB, and this was giving us ordered pairs, right?
Yeah, ordered pairs, correct.
So their order matters there.
Yeah,
When you do multiplication principle, AB is different from BA, right?
yes.
However, in this question, the meaning is not like that. The meaning is don't care about the order. You
Hmm.
have to do a by two, right?
Yeah,
Yes.
Yeah.
Next question is find the number of pairings pairings in a of a set of 2n elements of a set of 2n elements. So what is the meaning of a pairing? Pairing is a group of two, right?
yeah,
So for
Yes.
example, if the set is 1, 2, 3, 4, 5, 6, then an example of a pairing is 1 comma 2, 3 comma 4, 5 comma 6, this set. 1, 2, 3, 4, 5, 6 is one pairing. Another pairing could be 1, 3, 2, 4, 5, 6. This is another pairing. So basically, find the number of pairings of a set of 2n elements is find the number of ways in which the 2n elements can be grouped into pairs like this, right?
correct.
Okay. So now again here, technically here order doesn't matter for us. Like it 2 comma 1, 4 comma 3, 5 comma 6 is the 6 comma 5 is the same pairing, right?
Correct.
So you will have to be careful. This is the same pairing. These are
Yeah,
not this different. Okay.
correct.
You'll have to be slightly careful here. Uh, so how would you normally do the question? So you have to make pairings. So first pair, how can you make? Select any two out of the 2n, right?
Correct.
First pair you can make in 2nc2 ways, right?
Yeah, 2 and C 2 ways.
Right. Then after that pair is made, how many things are left? 2n
2
minus
and
2.
minus 2.
The second pair can be made in 2n minus 2c2 ways,
Correct.
right?
Yeah,
And
and so on.
similarly, third pair can be made in 2n
2 and
minus
minus.
4c2 ways,
Yeah,
and so on. Last pair, right? There
yeah.
are only two
Two
things
C
left,
2. Yeah, so one way.
and this will be pair number n, right?
Yeah,
This is the nth pair, right?
yeah.
So total number of ways in a normal way, the way I would do it is by multiplication principle now, right?
Correct.
The first pair, second pair, you have to make n such pairings, right?
Yeah.
So I will normally expect this to be the answer. 2n minus 2 C2
But
multiplied.
this whole thing by 2.
No, you have to be careful by what,
Mm.
right? It is not
Right.
necessary, it is always by 2.
Yeah, 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 yeah.
Like
Yes.
this is multiplication principle, say what is expected. So now let's simplify a little bit this one. We can let it be actually. Uh, we have to think now to what will come here. Okay, so we have to think how many times each pair is appearing. Okay,
Hmm.
like how many times is it being counted, right? So
Mm.
each pairing is counted how many times. So let's focus on some numbers. It will be easier if you understand it by some numbers, right?
Yeah.
So
Yeah.
1 2 3 4 5 6 is my set, let's say, right? And first pairing can be done in actually 2 and 6 C2 ways, right?
Correct.
15 ways to pair it, right? 15 ways. 62 is 15 or no, 10 it is, I think.
6 6 by 15 only.
Okay, 62 15 ways. So then what are the pairs possible? 1 2
One.
1 3 1 4 1 5 1 6 2 3 2 4
Two
2
five.
5 2 6 3 4 3 5 3 6, right? And 4 5 4 6 5 6, right?
Yeah.
How many are there? 3 3 6 3 9 2 11 4 15, right?
Yes.
Okay, I did my first pairs, right? This is the first pairing that I could have chosen. This is 15 ways, right? Then
Correct.
after that, four things are left, right? Four things are left, second pair, right? Second pair. That can be done in 4C2 ways, right? According to the question, according to the method that we have devised, right?
Yes.
So you have to you have to select any one pair out of this, right? So let's say my selection currently is I selected this as the pair, right? This one, 1 2, right? First pair, correct? Are you following what
Correct.
I'm saying?
Yeah. Yeah.
So after that, what is left for us? 3 4 5 6, right? Correct.
Correct.
Makes sense, no?
Yes, sir, it does.
So now there are 6 ways to make this pairing, right? So there is 3 4, right? There is 3 5,
Three,
there
five,
is 3
three, six.
6, there is
Yeah.
4 5, 4 6, and 5 6, right?
Correct.
Correct.
Yeah.
And third pair, like let's say we selected this, right? So 3 4, right? Third pair can be done in 2C2 only one way because only 5 6 was left, right? Correct.
Right.
Okay.
Right.
So now in the question, what we are doing is we're multiplying this and this and this, right? Correct.
Yeah. Yeah.
However, see how many times you are counting the same one, no?
Yeah. We are counting multiple times.
So when you're multiplying this 15 into 6, right? And into 1, right?
Hmm.
That you are getting 1 comma 2 is here, but see 3 comma 4 is here and
Yeah,
6 comma 4 is here.
yeah, 5,6 are there in all, like in the last three.
5 comma 6 is also there,
Yeah,
and
4,6 is in the second and the third one, and 4,5 and 3,6.
so many things you are counting many times, right?
Yeah, so but there's nothing
1 second.
clear.
Uh, 1 comma 2. Mm, oh, wait. This is happening only because I selected 1 comma 2 and listed out these only, right? If I had selected something else, I would have gotten a different listing here, no?
Right, right.
You understand?
Yeah, yeah.
Obviously, like I have selected one and listed
Yeah,
on,
yeah.
but I could
So
have
if
selected different one
select
and listed
and then,
different one,
yeah, got it. Understood.
right? So there are actually many different. Uh, 1 second, 1 second. Let me just think a little more. Uh, okay, I have to count how many times the same thing is coming. So I can already see that one particular thing has come 3 times here, right?
Correct.
Right?
Yeah.
And let's see in what other combinations that thing can come. How many other times it can come, right? Let's focus our attention on the one that has been repeated maximum number of times already, right? 5 comma 6 is repeated every time, right?
Apart from the first time, yeah.
Right.
Yeah.
So if I had selected some other one here, right,
Hmm.
I would have still, I would have still got this 5 comma 6 here.
Correct.
Hmm. Okay. 6 I would have still got. Okay, right now this is slightly unclear. The book is saying that each thing is repeated n factorial times. Each pair is repeated n factorial times. So the answer that we got, the 2nc2, 2n minus 2c2, and so on, 2c2, you have to divide by n factorial. However, right now it is not immediately clear why n factorial. Uh, each pairing is repeated n factorial times. Why? Uh, mm, okay, let's try to do this question in a slightly different way. Okay. Maybe this way is not really obvious. So let's try to construct a pairing. Let's say the set was what? 1, 2 till, right?
Correct.
Now, yeah, let's try to construct a pairing now. Uh, a pairing is a grouping into pairs like that, right?
Yeah.
So uh, let's say a pair having 1 as an element, having 1 as an element. Okay, one of the elements is 1, right? So the second element could be, what are the other options? How many options are there?
1 minus 1.
2n minus 1 options, right?
Yeah.
So,
Yeah,
so there are 2n minus 1 ways to make this pair, right?
correct.
Ways to make this, right? This first
Right.
pair, right? You have to make
Yeah.
n such pairs, right?
Correct.
Now, okay. So now let's say the selected element here is k, right? So the pair is 1 comma k, right?
Hmm.
And let's assume that k is not 2, right? Let's
Right.
assume that it is not 2, because if it was, okay, we'll just do the thing and then we'll understand what is happening. If k is not 2, then the next pair can start with 2, right?
Correct.
You cannot repeat it, right? So
Hmm.
next one can start with 2, and then how many options are left here?
2n minus 2. No,
No,
2n minus 3.
2n minus 3, right?
Yeah.
Because 1 and k and 2 has to be excluded, right?
Correct.
So 2n minus 3 ways to make the second pair, right?
Yeah.
2n minus 1 ways to make first pair, 2n minus 3 ways to make second pair. Now let's say this is L, right? And let's say
Yeah.
L was not equal to 3, right?
Hmm.
And the second one can start with 3, right?
Third one, yeah.
And this one will be 1, 2, 3, 4,
2n minus
5.
5.
So 2n minus 5 ways, right?
Yeah, so that means, so
We
okay,
can be
so we're
counting
getting the
odd
general
numbers,
thing.
right?
Yeah, on odd numbers.
Like this till 2n minus 5, and finally you can do till 3 and 1, right?
Correct.
This should be the answer. This is how we are constructing pairs. Now the reason why I was saying k is not 2 and all is obvious.
Yeah,
Like if
got it.
k was 2, then I would start
Then
with
we
3.
can't say the next one. Yeah,
I would start with 3 here, right?
correct.
Still the numbers will be same. It's
Yeah,
just
yeah,
that
yeah.
it's just that I'm counting in a slightly different way, right?
Yeah, that would make the analysis tougher.
I mean, not tougher. I would just, if it is 2, 1, 2 is a pair, then I will start with 3 here and say this is L, right?
Yeah,
Still, it can be, the number is same, right?
yeah.
The number of possible options for this is still 2,
Correct, correct. 2n minus 3.
right?
Yeah,
So,
yeah, yeah.
so number of possible ways was 2n minus 1 here, 2n minus 3 here, 2n minus 5 here, right?
Yeah.
And so on, you make n pairs. So this will go on till 2n minus 2n minus 1. This
Hmm.
will till 1, right? So this is the answer. Now, let's think of, so our answer is coming like this here, 2n minus 5 till 3, 1. And the earlier thing we were seeing was 2n C2, 2n minus 2 C2, and so on till 2 C2, right?
Correct.
Let's see the relation, 2n factorial by 2n minus 2 factorial, 2 factorial, 2n minus 2 factorial by 2n minus 4 factorial and 2 factorial. And this one would have been 2n minus 4 factorial by 2n minus 6 factorial, 2 factorial, and so on till 2 factorial by 2 factorial, 0 factorial, right?
Yeah,
You're saying this and this is getting cancelled throughout, right?
correct.
So what will be left is each one is giving a 2 factorial, right?
Yeah, so
So
2n.
2n factorial by 2 factorial power n, right?
Yeah,
So that
Yeah.
is equal to 2n into 2n minus 1 into 2n
2n minus 2
2n minus 3,
up to
3, 2, 1
1.
by 2 power n, right?
Correct.
So now
Yes.
see that you can isolate all the even odd ones, right? So that will become 2n minus 1, 2n minus 3, and so on, 3, 1, right? Isolate all of them. And 2 power n divided by the even ones, right? Right?
Yeah.
So 2n into 2n minus 2, so on till 2 divided by 2 power n, right? So cancel 2 power n from there, and that will be n factorial. No, see, n minus 1 till 1, right? You're understanding?
Yeah.
This becomes n factorial, no? N factorial into 2n minus 1, 2n minus 3 till 3 into 1, right? Are you getting the n factorial part, how it came?
Yeah, got it.
So basically what we saw here is that this thing that we had earlier thought, multiplication principle basic, is n factorial times what we expect the answer to be. So the
Correct.
is correct when it's saying that divide this by n factorial. This is the same as 2n c2, 2n minus 2 c2 into 2 c2 by n factorial. Okay. So number of pairings here, it is here you're exactly constructing the pairing, like thinking of, if I put 1, then what choices I have, and then second pairing, how many choices I have, right?
Yeah.
So you're
Correct.
actually constructing the pairings. Here you were thinking of selecting any two, then selecting out of the remaining and multiplying. But it is likely that we have many repetitions here, but it's hard to think of why the repetitions is n factorial. So
Yeah.
this one is slightly easier to get.
Yeah.
However, the answer is same. Okay. What we will do next is some geometrical applications of this, of combinations. So things like out of n points, how many lines can you make and stuff like that. So
Mm-hmm.
there are a lot of geometrical applications, but I think we should stop here. We'll continue from this point onward in the next class. Okay. So things like number of points of intersection of n non-current, concurrent, and non-parallel lines. There are n lines. This is concurrent. Suppose
Yeah.
there are n non-concurrent, right, and non-parallel lines, right?
Mm.
Number of intersections will be what? Take any n, select 2.
Correct.
See 2 intersections.
Yeah. Yeah.
Number of intersections. Similarly, number of lines that can be drawn passing through any 2 points out of n given points, in which no 3 of them are collinear. So suppose points are given, right? Number
Yeah.
of lines that can be drawn. Here, no 3 points are collinear, right? 3 points are collinear means 3 of them lie on the same line. Nothing like that is the case here. So number of lines that can be drawn will be NC2 here, because 2
Yeah.
points will define a line. And N is 5 here. So 5 C2 lines can be drawn here, right?
Correct.
5 C2 or almost 10 lines can be drawn, right? You can actually draw them out, right?
Mm.
I don't think we are missing
Correct.
any now. 1, 2, 3, 4, 5, 6, 7, 8, 9,
Yeah, there are 10.
10, I think.
Yeah, there are 10.
So basically, as long as 3 points are not collinear, you can make NC2 lines, right? Similarly, suppose there are n points. How many triangles can you make? Obviously, NC3. As
Yeah.
long as any of those 3 lines are not collinear. If 3 lines are collinear, then they cannot make a triangle, right? So you
Yeah.
exclude those 3 lines, those 3 points, and make triangles out of the remaining, right?
Yeah.
Correct. So similar questions, what we will see, we'll continue from this point. Okay. So there are geometrical applications for this, and sometimes questions are there where you have to count the number of lines, sides, things like that. Okay.
Yeah.
uh, that
Yeah.
will be the last portion for combinations. So this is the geometrical applications and all are the last bits for combinations, after which point we will be looking at permutations. Okay.
Okay, sir.
uh yeah, so that's all for now. Let me know when you want the next class, we'll schedule it.
Yeah.
Okay.
Yeah.
Sure, sir.
Bye.
Okay,
Bye.
thank you, sir. Bye.